All right, let's finish chapter 12 with 12D, which will focus on velocity and acceleration along a curve. Um, the position of a particle is a vector function, and so will the velocity and the acceleration. Being vector a time vector function, um, to determine the velocity, you would differentiate the respective components, and you will do the same with the acceleration. It will be the second derivative of the position vector components, or you can just differentiate your velocity function as you would do normally. Okay. Additionally to that, as we deal with vectors, keep in mind that when you do the modulus of a vector, you will get the magnitude. So as a definition, the speed will be the magnitude of the velocity. So you will have your velocity function, and you will have to take the modulus. To find the distance between 2 points, you can't just take the modulus of a vector position. What you need to do is to determine the shortest distance between 2 points. You do the difference of the two vectors. That will create a new vector, and by taking the modulus in turn, that's how you will get the shortest distance between 2 points. Also, don't keep that in mind. I don't think we're gonna have many questions in here, but keep in mind also, if you want to find the distance along the curve, which is kind slightly different between 2 points. So you find your between 2 points, you will have a different path. If you want to find that distance, you need to anti-differentiate um, uh, this new function that is created from, you look at your you get your vector position, you differentiate each component, and you apply this formula. So you square each component functions, you square root the sum, and that will give you a new function that you should be able to anti-differentiate just in terms of the t variable. Alright, so it's a slight different process. Just be mindful of the difference between the two distances. Direct application of that, you have your vector position in terms of I and j with two components. You differentiate respectively to get your velocity vector, your acceleration vector, and also to get the speed, we in part A we calculate the vector, we get the modulus, and we get a new expression for the speed. Alright, let's continue with example 16. So you have a different position vector function. You need to determine the velocity, then the speed, then the minimum. So to determine the velocity, you just differentiate the respective component. For the speed, you will take the modulus. You end up with a new vector function, a modulus function, which is a function of time. Now, to find the minimum, what you could do is differentiate, solve for that derivative equals 0 and find the t value and substitute. But here, because it is a quadratic under the square root, a quadratic is a parabola, it will have a turning point. In this situation, the turning point is going to be a minimum. So to make it quicker, what you do is you extract this quadratic expression, and you will need to find the turning point. So to find the turning point, you just complete the square and do find the turning point. Before you do that, what you will do, you factorize 8. You will end up with a fractional forms, which shouldn't be a problem. You complete the square, you get the turning point form, and expand it again. And with the turning point, what you look is that 9/2 will give you the minimum value of that expression. We go back to the speed expression, which has a square root. So the square root of that 9/2 you simplified, that will give you the minimum speed. Okay. Also, when do you get that value? This is extra, but to find when t is equal to 5/4 is basically that when you have that turning point form, that left component will be equal 0, so it's make that equal 0, and that gives you the t value. All right. Next, a little bit of more of a worded situation. So read the problem and pause the video and have a go at this. Alright, so with part A, so you have a vector position function. First part asking you the time it takes to reach the ground again. Looking at your vector position, all you need to do is the j component, which is the vertical component, make it equal 0, which indicates that the particle or the projectile is back on to the ground level where y equals 0, which is a quadratic equation in terms of t. Here we can easily extract the highest common factor. You end up with two values. So t equals 0 is going to be your starting value, and when t equals 100 later on, that's when the projectile is back on the ground. To find the speed when it hits the ground, so when t is equal 100, so you're gonna have to use that t value from part A. To get the velocity, you differentiate, then you take the speed. Oh, hang on. So what they did is they already substituted t equals a 100, so we get the actual velocity when it hits the ground. We take the modulus of that to get the speed, and that will be the answer. To find the maximum height, let's go back to the velocity function. In that situation, when it at a maximum height, what you do is the vertical component is equal 0. It means that you will reach the maximum height, which is a simple linear equation in t equals 50, which makes sense for a parabola, which is half the time to go back to hit the ground again. You substitute into the position vector in the j component, and you end up with the maximum height. And lastly, initial speed, you take your initial your vector function of the velocity, you substitute t equals 0, you evaluate it, then you take the modulus, and that will give you the initial speed. Alright, I'm just gonna move a little bit quicker with the next examples. You have a position function. You need to find the velocity. Oops, let's go back. You need to find the velocity, so you will have to differentiate. B, you will need to take the modulus of the part A. To find the maximum speed, you will have to analyze the speed function, as well as the minimum. You need to look at the speed function. Alright, so we have the derivative of the position vector function. We take the modulus, which is root of 12 cos squared plus 8. To find the maximum and the minimum respectively is looking at the range of cos squared. So cos is from -1 to 1. You square that function, it's going to be from 0 to 1. So 0 is the lowest value that gives you your minimum, and 1 is your highest value that gives you your maximum respectively. So you get root 20 and root 8 respectively. Alright, last example. So have a look at this situation. I think we covered a similar example in a previous session. So you have two particles, they have respectively two vector functions. You need to prove that those two particles collide while traveling at the same speed, but at right angles of each other. So you will have to determine the you differentiate the position vectors at a specific time. You need to make sure they have the same position. You get the modulus of those velocities and check that they are the same. And to find that they're right angle, you look at the two velocity vectors, you do a dot product and make it equal 0. And it has to be equal 0 at that instant and at those positions. So the two vector positions that need to be equal, you will solve that for t. They are two respective, a cubic and a quadratic equation. You will take from equation 4, which is a quadratic that you solve, that give you two values for t. You will check from the original equation if it matches, you make those equations right. As the first one doesn't work, it only collides when t equals 2, as you will have the same positions. Then what we need to do, we differentiate respectively and we substitute for t equals 2. We get the modulus respectively for each one of them. They will have the same value, so we know the speed is the same. All right, and then with those two here, let me get that laser pointer. So this is the velocity when t equals 2 for particle A. There is the velocity. Hang on, I think there's a little bit of a typo here. It's actually the velocity for particle B. You will do a dot product or a scalar product of those two. You evaluate it and simplify that equals 0. Then you can conclude, as you write a sentence, the particles are traveling at a right angle at the time of the collision as it was used. You use t equals 2 for that. All right, so I think this one is going to be the actual last one. So pause the video, have a go at this. You will need to find you will have to do two different calculations. The first one, you will have to anti-differentiate along the curve, so you will use the travel along the curve formula. The next one, you will have to we'll get on with it. Okay. All right, so with the first part, you apply the formula, which is this one for the distance traveled. You differentiate, you substitute, and as it is asking you for an answer to 3 decimal places, just use a CAS calculator. You might look at it and quickly think if it is possible to anti-differentiate by hand, but in this situation it isn't, so it will be just to use technology to your advantage. Alright, with part B, you need to find the shortest distance between the 2 points. So when t equals 0 and t equals pi on 3, you evaluate those two vectors. Then you do the difference of the position vectors. From that, you get the modulus, and that will give you the exact answer of root 15 over 4, which should be the answer. You don't really need to round it up. It's probably, if you estimate it, it's to compare your answer to part A. And that's it for 12D and chapter 12, and I'll see you next time.